Hmm. Good morning, everyone. My name is Akina Parker. I am a hydrogeologist at GEOSS via groundwater on something Kafri based Stellenbosch. And today I'll be taking to you about the hidden but vital resource that is groundwater along the West Coast, with a particular focus on groundwater monitoring in the Greater Savannah region. Here we. So for those that don't know, 97% of the total water on Earth is sitting in our ocean, the sailor. 3% of that is fresh water, and then of that 3%, there's 29% that is stored underground as groundwater. So groundwater bearing formation is what we call the aquifers, and you get different types of aquifers. So one that we see mostly in the West Coast is your intergranular aquifers. So these are your sandy aquifers. We also refer to them as primary aquifers. You then also have fractured rock aquifer systems in the area. And this, for example, is your granite with cracks and faults. And then one that is less common in the Western Cape, there's karst systems. And that's an example of that is your limestone with cavities. There's a lot happening here. So on the right-hand side map is what we call the superficial geology of the area. So what is lying on the surface? There's lots of colors, but essentially it's just different types of sandy formations. And then along the coast, if you drove the West Coast Road into Club Mykonos today, you would have seen the granite poppies that come out on the cliffs. But if we look from a ground to bedrock aquifer structure, typically what we see is your upper aquifer unit that is separated from your lower aquifer units. Both of them are intergranular, and it's separated by what within an aquitard. So an aquitard is what the name suggests. It's a layer that retards the flow between the aquifers. So in general, it's clay. In the area, it's fairly discontinuous. In some areas, it's quite thick. In some areas, it's virtually non-existent. And then underlying this lower aquifer system is our bedrock. And depending on where you are within the region, it's either your Malmesbury shales or your granite. So there are a few aquifer systems in this area. However, I'm going to talk to two. We'll chat to the others a little bit on very briefly, but the two major interconnected aquifer systems is your Langebaan Road aquifer and the the Elandsfontein aquifer. Excuse. So the Langebaan Road aquifer system is demarcated by the yellow line, and then your Elandsfontein aquifer is demarcated by the red outline. And how these aquifers formed was through paleochannels from the Berg River's former course. So it deposited coarser gravel material that is preferred groundwater flow paths. So what the map is actually showing is depth to bedrock. So the paleochannel sits in the thicker portions where there's like a deeper depth to bedrock, and it's indicated by that purple bluish color on the map. So overlying these aquifers are situated between them, you had two municipal well fields, amongst other groundwater users in the area. For two municipal well fields, the Langebaan Road well field, which is indicated by the yellow dots on the Langebaan Road the Langebaan Road aquifer portion. And then you have the Hopefield Halfwall situated west of Hopefield, just on that fringe of the upper limb of the Elandsfontein aquifer system. And then on that southern limb in the center, you have the Crops Elandsfontein phosphate mine, and that's the polygon in the middle. Generally, recharge to the area is largely through regional processes. And from high-lying areas further afield, you also have fault systems that are running through that's bringing water. But you do have a localized component of recharge. It's just on a smaller scale. And how the flow paths work is the groundwater, full aquifers get recharged. It flows past the well field and then discharges into Saldanha Bay, and then also into the lagoon at the southern tip of the lagoon, which we know that's go. So there's a lot of uses, and this is by groundwater monitoring is quite important from the area. And what makes groundwater significant as well is, as we know, the lagoon. It's a Ramsar site. and the fresh grounding to inflows sustain the ecology in Milavuri. So these inflows have allowed for unique plant and animal species to develop in the area. And it it's quite a fascinating case because you the lagoons, it's typical of an estuarine environment where you expect a river to be. So you find it at river mouth, but obviously we know there's no river via the Curved River is up on, there's no east. So it just highlights the vital importance of monitoring in Pereira as we have quite a dense monitoring network between the lagoon and the Berg River of different boreholes. So it draws into the upper aquifer, some even into that aquitone, and then into the lower aquifer as well. So a range of boreholes. And then if you, by zooming quickly just to between the mine and the lagoon, you can see they cover quite a big area, Gituin as um, and if I can just touch on number of boreholes for a bit, there's 19 municipal law built boreholes, so that's abstraction boreholes, both from the Langebaan Road and Hofield Wildfields. And then you have 30 dewatering boreholes at the mine. And Mark will touch on this later, but for those who don't know, what happens at the mine is they do water to keep it dry, and then they re-inject almost 100% of that water back into the aquifer system to sustain the flows to the lagoon. So outside of this, we have 61 dedicated monitoring boreholes situated strategically around the abstraction points and also along the Halio channel. Um, and then we have 5 dedicated boreholes in the Hillbeck area as well in the national park. And due to the sensitive nature of the system, we monitor boreholes for rooted levels and then general chemistry, which I'll chat to a little bit later, monthly. And then we sample for a larger chemical data set in microbiological parameters on 4 key bases. So to give you an idea of what a monitoring graph looks like, as I mentioned, we monitor water levels on a monthly basis, but there are quite a few boreholes that also have sensors in them, and they record water level and temperature at a specific interval. It can go up to 1 second readings if you wish. And then majority of the time, we're doing manual readings on a monthly basis. So that's indicated. I don't want to use the laser pointer because then I'm going to choose which one. Um, but it's indicated by the orange triangles on the bar. So that's your beta level. The left axis is your meters below ground level. So that brown line on top is ground level. And then the left axis is meters below ground level. And then on the right hand axis we have electrical pond activity. And what this is just a measure of salinity. It gives a general indicator of the general chemistry of the water. So it's quite a nice indicator. And we look at this monthly, and then as I mentioned, Porky, we even a nice for larger chemical data set. What's really nice in the area is that there's quite a few walls, and a lot of them have lots of data that DWS has collected over time, some predating the 1970s. So we use this data to analyze trends, and it's really nice to have time series data because we can see what happens to the aquifers or boreholes when the well fields were commissioned, for example, when the mine was commissioned. So it's really informative to have this information. And then to talk about the mine quickly, it's what you have on the screen over here is your pre-mining water table. So it's a cross section, right? Between up gradients of the mine through the pit towards the Langebaan Ding. And it's showing pre-mining water table indicated by the green stipple line, and then the current water table, which is indicated by the blue line. And what we can see is that the water levels up gradient, so around SMP 12, that ball that's on the right-hand portion of that bar, it's stable, pre and post, or not post-mining, or current full step. And then you have this localized dewatering effect in the mining area. And as I mentioned, they take almost 100% of that water and re-inject it into the 20-bore ejection line. And just south of that, at around SMP 7, SMP 8, SMP 9, as you walk down the profile towards Kilbeck, you can see a rise in water levels. And there's no mounding of water levels, which is a positive indication that the aquifer is accepting data and that this injection scheme is actually quite successful. And then as you move further down gradient towards Kilbeck, before mining commenced and current water table, it's safe. We don't see any negative impacts, not just of mining, but any upgrade and extraction activities that take place. If I can quickly just show you the data for one of the philitic sites. So this is a borehole, we call it philitic 1, situated right at the tip of the lagoon. And what you can see is basically a straight line over time. So what I've done is I've zoomed in a little bit just so that you can see the fluctuation. So that um, left-hand side water level range is a 3.5-meter range, just to really zoom in. And you can see that there are seasonal fluctuations in water levels, but that there's no negative long-term concerning trends or impacts that we see from upgrading groundwater species. And then what's really interesting, because this ball is so close to the lagoon, which is really saline, I'm sure most of you have swam in it before, but the electrical conductivity at this ball, that the range of values is it's between 100 and 150. And to put that into context, the drinking water standard for electrical conductivity is 170 millisieverts. So this is sitting well below that, which just evidence that there are this fresh groundwater inflows into the lagoon that we need to maintain just to make sure that it keeps supporting the ecology. So in summary, the West Coast hosts vital ecosystem that support industry, ecology, and humans. And despite despite groundwater users in the area, we see seasonal variations in water levels and chemistry. But based on the data set that we have, we don't see any negative impacts on the lagoon as of yet. But monitoring will remain critical because it is such a sensitive area. And we need to make sure that with industry expanding, with the continuous abstraction, with the mining taking place, that the aquifers are kept healthy and that the flows to the lagoon are sustained. Thank you so much. That's me. I'm going to give over to Kobe.
Good morning, everyone. Please excuse me, my English takes a while to warm up, but I'm going to try my best. But like Akila said, my name is Albie Charles. I'm also a hydrogeologist at GEOSS South Africa, and it's my first year attending the Open Day, so I'm really grateful to be here and to tell you more about conceptual and numerical modeling and what that entails. So as an introduction, the area is quite special. The Saldanha Bay region has been the focus of extensive research for several decades. So we have a large data set, and the fast studies and also more recent studies has generated this rich set of data and also conceptual frameworks and numerical models focused on this Miller-Berg River aquifer system and its subconfidants. And these are the Adam Bushgrol aquifer that is situated more towards the north of the Berg River. And then we have our Langvan Road aquifer, our Elandsfontein, and then also our Grootwater aquifer more to the south towards Eiserhoek. And just to explain briefly what a model is, so simply it's a mathematical equation. And in the past, it was solved by hand, which is wonderful. But today we have smart and sophisticated software to help us. And what we do with models is we try to quantify how much groundwater there is and how much is available to be utilized. And also when we sit in stress conditions, like the drought a couple of years back, and also as abstraction increases, it's an important tool to be able to help us to inform our planning and decision making going forward. So this timeline just highlights some selected milestones in this ongoing research journey. And this is not an exhaustive list. There's been many, many more research and studies done over the years. But it shows the responsive nature of this work. So the successive studies build on one another as our understanding grows and also as our awareness grows of these bound species. So yeah, due to rising and increasing demand, climate variability, and also increasing pressure on our surface water resources, the Saldanha Bay local municipality, they turned to groundwater as a critical long-term source of supply. So their Langebaan Road, wellfield, and also their Hofield wellfield form a core of their groundwater supply need. So their Langebaan Road wellfield was developed in 1998 and active abstraction started in 1999. And the Hofield wellfield was only developed 2 decades later. And I also wanted to highlight managed aquifer recharge, and this is artificially replenishing our groundwater resources. And the study started as early as 2008 and 2009. And these methods, the feasibility thereof, was later investigated for the Egansfontein mine, and it's currently actively being implemented. So, as mentioned, the Hopefield valve field was only later developed between 2018 and 2019. And following licensing of this water use with the Department Water and Sanitation, the municipality is required to construct and update a numerical model to be used as a management tool. So just to give an overview of our model domain of our study area, and as you can see, it is quite a large area. It covers a wide piece of land. And this is to incorporate the regional flow processes that Aquila referred. However, when we investigate the well fields and the mining operations, we zoom in quite a bit to account for local processes in Rodiva. So, Aquila mentioned this before, but groundwater occurrence and flow in the area is mainly described in the context of these macro-scale geological features. So we have these paleochannels that Aquila already explained, which is deeply incised channels in the bedrock that's filled with sandy deposits. But we also have these fault structures. And I showed the Colenso fault on the map, and it expands from Franschhoek right through the model domain. And although it's indicated as a single stippled line, the area it influenced is quite extensive, like up like several kilometers. And it's quite special to see it in the field as well. But these fault systems are associated with large-scale fracturing that can cause deep range of field that is pulled about. Sorry, there it is. Okay, great. And as I said, there's been various mapping strategies over the years to try and delineate the shape, the size of these failure channels, just because it's so important in terms of groundwater flow. So I included 3 examples of scientists, their interpretations of how these paleo channels look and how it evolved over time. And only quite recently, the Department of Water and Sanitation also published a new interpretation of how these paleo channels look. So if we take a closer look at the municipal well fields, you can see it not only consists of the production borers that's shown in the green dots, but it also consists of this monitoring rig. And we're very fortunate to have a long-standing monitoring record for these borers to be able to track trends and also to assess impact at the end. So that they will feel okay. And then I quite like this quote by Sherlock Holmes. It says, data, data, data. I cannot make bricks without clay. And it highlights the essential role of data in making informed decisions. And without it, we cannot make logical and accurate conclusions. So what we do is we use our knowledge of the geology, topography, rainfall, and boreal information, just to name a few, and we use it to conceptualize the system. So a conceptual model is a simplified version of reality. So that's the figure shown at the bottom right. And it's a summary of our current knowledge of the system and also the prevailing processes that influence that set. And we use our knowledge of the geology to simplify these hydrostratigraphic units just basically aquifers or aquitars, like Aquila said. And it looks very simple on the figure. I can assure you it's not as simple as just a 4-layered system. In reality, it's much more complex, but for our understanding, we try to break it down and to understand it better. So the area is known for its upper aquifer unit and also its lower aquifer unit. And these are intergranular aquifers, so porous media, and the water flows through interconnected pore spaces. But then we know the bedrock shale and granites in the area can also act as aquifers where it's scratchy. So the water flows through cracks and fissures. And Akila mentioned this before, sorry for if I explain it again, but in terms of how ground is recharged, it's either local or regional processes. So locally, it can be recharged by a direct infiltration following a rainfall event. But then we also have these regional processes, which is very important. And is possible recharge even via these fault lines, as shown on. So how does one go from a conceptual to a numerical model? And as I said, a conceptual model is a simplified version, and a numerical model is a mathematical model, and we solve it using computational methods. So what I've shown in the picture is just an example of a mesh that is generated in a commercial software package FIFLOW, and this model is for the municipal well fields. And then this is also for the mine, the model that was created for the mine. And as you can see, there's much more detail surrounding recreation. And think of a mesh as a net or a grid. So what the software does is it solves the equation at each of these individual elements or triangles. In some softwares, it's grids, squares. And then it puts it together piece by piece to simulate flow throughout the whole area. So it's a quite powerful tool. And then also this mesh can be extended underground to get a 3-dimensional view of what the aquifers look like. And as you can see, it is simplified based on those hydrostratigraphical units that I showed earlier. Yeah, so as I said, numerical modeling is quite a powerful tool in groundwater resource management. And just to show you a couple of examples of how it can be applied. So in this case, it can be used to evaluate the effectiveness of the dewatering and injection scheme at the Elandsfontein mine. So the colorful picture shows the drawdown cone around a dewatered pit. And the models can also be used to simulate or predict. So it makes predictions into the future. And then we use monitoring data, so data that we gather from the field, to see how well the model performed at the end of the day. And in that way, we can update and train a model to make even better predictions going forward. And then in case of municipal welfare obstruction, it can be used to quantify aquifer potential and also the impact that large-scale obstructions can have under stress scenarios like the drought. So I included an example from a previous study that was done, and it shows the cone of depression, so the drawdown cone under different obstruction scenarios. And this is very useful in terms of the for the municipalities' planning purposes. And as I said, monitoring is then essential just to see how well the model performed and then updates them. So I just wanted to make some closing remarks. So we cannot predict the future, but we can use models to run scenarios based on our current understanding and also anticipate the changes over time. And just remember, so like I said, the conceptual model is a simplification. So it's impossible to bring in all the complexity of a real world system. So we make assumptions, and the model relies on input data, on what we measure in the field. So there are inherent limitations, but nonetheless, it is such a powerful tool to be used to inform decision making. And then, as I said, ongoing monitoring is so critical just to validate the performance of the model and then also to periodically update and decode that. And thank you. That's all from my side. I'm going to give over to you.
Good morning, everybody. It's a great privilege to stand before you this morning and to present our story. And it is, I get excited when I listen to the passion that comes from young scientists who have taken real world challenges and convert into practical applications that ultimately allow for the advancement of us was a nation and as it was humans, but at the same time with their custodianship towards environmental stewardship. I'd like to share with you just Fontain's story, and then delve into how the practical meets the science, because that's really what has happened with the mine development. It's really showing very clearly how science matches engineering and how we get ourselves towards producing and producing equipment and processes that allow us to meet our objectives. But let's first have a look at why crops. Crops is a mine that is mining a resource that is essentially it's a mineral, very important mineral in our lives. Some of us, and I certainly wasn't before I started in the world of phosphate, wasn't aware of how important phosphate actually is. But phosphate is one of the three key ingredients that goes into the production of fertilizer. And in terms of fertilizer production, 85% of rock, and this is a bit of a misleading term that is used in the industry. When you talk about phosphate rock or phos rock, it's actually not rock, it's sand. And it is a very misleading term, but we talk about it anecdotally about as phos rock. So 85% of all the world's rock production goes into the production of fertilizer. And certainly we see it and it's ongoing that demand and prices continue to rise. In terms of world resources, it's a one renewable resource that is declining. 30 years ago, the resources that were available and the quality of phosphate deposits were in a totally different space where they are today, and certainly from a quality perspective. And that coupled with what's driving it, just some interesting stats with regards to sub-Saharan Africa. Certainly expanding population, we know that diets are improving and the demand for better quality foods. Generally within Africa, compared to the rest of the world, the use of fertilizer was a lot lower in terms of total distribution of fertilizer per hectare of arable land. And what we see was a staggering statistic that the food demand from sub-Saharan Africa alone is likely to triple by 2025. And therefore, the only way that can happen is increasing wheels and agriculture. That only happens through additional circles. Crops, what's the opportunity with crops? It's a local resource. It's in a ramp-up phase. There is always, and there has been, and it's consistent, a general global shortage of phosphate. What's unique to our deposit, which is a sedimentary deposit. So you get two types of deposits geologically. One is a sedimentary deposit. The other one is an igneous deposit, which is a hard rock deposit. This is a sand sedimentary deposit. It has formed through the progressive washing and deposition of sands through alluvial methods or marine techniques. It is a low cadmium reserve. Why is that important? Cadmium, we know, is a carcinogen, and it does occur and it passes through fertilizer. And when it gets added to fertilizer, it passes through to the plants which we consume. And we know the tragedy that cancers lead to us in our daily world. We have a great geographical advantage in compared to where we are locally. We are relatively close to a port, and we participate in the small traded market of generally in phosphate operations. Fertilizer operations are directly coupled to a downstream fertilizer manufacturing facility where they feed straight into a chemical what we sell in this market of phosphorop, which is generally a 5 to 70 market. Now here's an interesting, I'm not going to delve nearly as deep into the mathematics or the chemistry as regards to what's going on in phosphate, but just to show you there on the bottom, that simple chemical equation is what we are producing. But to get you to your NPK fertilizer, we will need to follow through that chemical process. And typically what happens is you add sulfuric acid. Sulfuric acid converts the phosphoric into a phosphoric acid, and then you add further to that nitrogen to add and then you land up with what is commonly known as MAP and DAP, monoammonium phosphate, diammonium phosphate, which then becomes one of the next phase in fertilizer production. And by adding potassium, you then land up with your NPK. So typically you would know that if you purchased it in a nursery, 321 or 323 is typically what you used. Now, the quality of phosphate that we produce is used as we refer to the percentage of P2O5. P2O5 is potassium pentoxide, which is just our reference to phosphate in simple terms. And the chemical table reports as phosphorus, but we talk about phosphate. We produce a quality of 30%. So it occurs in the ground at a quality level between 5 and 10%. We upgrade it to 30%, and 30% then becomes the acceptable quality that the downstream producers and chemical conversion processes and then take it and convert it into a soluble form. That's an important point as well. What is produced is largely insoluble. So you can take it and it won't present all different to dry sea sand when you look at it. And if you put it in a cup of water, you measure the quality of the water before and after. The percentage of P or orthophosphate, PO4, and won't be high concentrations. It's very insoluble in its natural form. It requires a chemical conversion in order to make it soluble. That's how the nut is cracked to make it and convert it into phosphoric or monoammonium phosphate or SSP, single superphosphate. As I say, that makes our product and certainly our deposit interesting and attractive to world users is that it's low in cadmium, meets EU standards and future standards with regards to cadmium. It also is very low in radioactivity. Radioactivity is a problem area as well, and that also is an area we are low in, and it meets the gypsum EU standards. Gypsum is used and they produce as building material, and the radioactivity that occurs there is also an important thing to track. Overall, our product, because it's of a sedimentary nature, generally you compare it to an igneous deposit, would use a lower amount of sulfuric acid in the production or downstream phosphoric acid, which makes it attractive. And then as a result of that, you also produce less gypsum, ultimately in the process. Where are we located? If you haven't, you're not sure, we're sitting almost equidistant between the R45 and the R27. In that triangle, we are adjacent to the national park, and the deposit is indicated in that gray hatched area that you see there, which is where the physical deposit with mining right is actually demarcated as the entire triangle. So the triangle indicates what the mining right it covers. A couple of key features here which make it advantageous. We are within 40 kilometers to the port, so the access using the freight corridor that Lindsay referred to, we use the R35 to take us into the back of port area. We have storage facilities for our product, and we use the Nautic Port Terminal. And it is situated also, as the crow flies, to the shoreline about 8.5 kilometers to the actual lagoon. Now our story. As of next year, would have been on the West Coast for 10 years. And I joined the mine in its early days. It was really greenfield stuff. And it's been an incredible journey. My entire career is in mining. And this has been a journey that I'm proud to have been followed. Just to take you through some of these are headlines. 2013, we started with prospecting. In 2015, we were awarded the mining rights. We put together the definitive feasibility study for the mine. 2016, we started with our construction paper when I joined. In 2017, the water use license was awarded, and the provisional air emissions license was also indicated. That no sooner had we started in 2017 than we had to shut the mine down within 3 months of starting up. And there were a number of reasons for that. Economic conditions were very, very difficult at the time, and also the metallurgical process that had been adopted needed to be modified. We realized that we were not able to achieve the quality that we were hoping to do, and the process was not robust enough for us to maintain the quality at the rates we needed. So we had to go into a refunding phase. In the period between 2018 all the way really up to 2020 was refunding, redrilling, additional test work in order for us to refine the process. And after we'd done that, we managed to raise the necessary funds, appoint the construction company to then proceed. Our EMPR was upgraded, and we continued in 2021 through the period of COVID with what we called our optimization phase. So we optimized the process, and through 2021, up until the end of 2022, we did our second phase of construction. Then we commissioned the mine in December of 2022. And since then, we've been busy with the ramp-up phase in 23, when we started our marketing and sales and development. And what's been exciting is that we have recently coined, and it's an acronym that drives us. We say all phosphate out the gate, and therefore we look for markets. We've seen the demand for phosphate. We see the requirement for it. So we're driving heavily to say, how do we get phosphate that we're pulling out of the mine, get it out to the marketplace, with the markets so desperately needs it. So we've developed what we call our nanophos product. Nanophos was originally a waste stream. It's not the highest quality phosphate, but it is an ultra fine product that has been identified as being good for soil conditioning and soil strengthening for the agricultural market, in particular the local market. There's a lot of interest that's developing is in the local market. We are working on developing products there using that nanophos product, because the ultra fine material that we have in the product actually makes it more susceptible for slow release phosphate. I said to you it was largely insoluble, but as you apply it either with an added mineral or an added coating to it, and you distribute it into the soils through the conventional means, and the soil is possibly slightly on the acidic side, so it's below the 7 mark, we see that over a period of 3 years, the phosphate is then released into the soils, and we manage to sustain the soil health. But generally, the downside with your soluble phosphates or the soluble fertilizers is that the plant had a very narrow window that it must get that fertilizer into its root structure. Otherwise, the phosphates are washed away into the dye. So that is in short, our journey. Couple of headlines. We have 43 kilometers from pit to port. Great road infrastructure that's been made available by the local governments and the local municipalities. We have secured, of the 8 million tons that Lindsay referred to in terms of the multi-purpose terminal, we are around about a 10% user of that. So we use about 10% of the multi-purpose capacity, multi-purpose port that is. We have Eskom supply directly to our mine. We have a water supply that comes off the West Coast District Municipality supply. We do not use potable water from the pit as the predominant usage of water. There is a small amount of water that occurs in the pit, and we'll take you through it now, but we laid a dedicated supply line of potable water to the mine because we did not use any of that for the mining processes. We're 9% ownership of the South African ownership. The predominant shareholder is African Rainbow Capital, and they are a great shareholder that supports us through the difficult periods that we've been through. And just some interesting labor stats, 540 people are employed on a full-time basis. In terms of those that are from the Saldanha Bay area, 93% of the apprentices in the Saldanha Bay area. And where do most of either the people reside? 44%. We made it our mission to say Hopefield becomes our center of focus. You would have seen Lindsay's slide that good towns within the Saldanha Bay municipality in order of importance. What was number 4? It was Hopefield. Hopefield sits there. And so generally, that when we came into the area, we were faced with a term that was very quickly used and repeatedly reused. We spoke to people from Hopefield. This is the Weeskinders van die Weskus, was what we were told. And I think that has changed. There's been a change in the overall mood and enthusiasm within the residents of Hopefield. And so we are proud to say that 44% of our employees come from Hopefield Bay. And then the other WIM statistic is classified, it's a mining term called women in mining. Because traditionally mining was a male-dominated industry. And there's a general target that mining industries try and target. 50% is the target that's put out for industry to achieve. We're tracking on the higher end compared to our competitors and compared to other mining industries in this country at 22%. Or for people on site, a warm memory powder burr. And they make a great difference. The drivers of our biggest trucks are latest, and they do a great job. They look after them a bit than me. So just to take you and to join now the practical science with how we actually run and operate a managed aquifer recharge. To state clearly again is that we are not using the groundwater. The design was predicated and the mine's permits were based on the fact that we were to prevent or impact on the aquifer, not to use the aquifer water because of it all sits within a ground controlled water area, and that we needed to mine the pit safely. On that stratigraphic column that both Katila and Albi reflect showed, if you lay the water table over that, you will see that the phosphate deposit, which is called the Mais Onfontein Kelator formation, is underwater, and it would not be able to be mined unless the area is correctly dewatered. So we needed to dewater the pit. Mine was in order to mine it safely, and dredging wasn't the option what we could apply. We operate within the upper aquifer. You'd have seen there's an upper aquifer unit and a lower aquifer unit. And on that slide, the green dots indicate the dewatering borehole network around the mining pit. And initially started off with 36, and we've reduced it down to 28 more efficient boreholes. The water that's then pumped out of that ring is then re-injected into the pink boreholes that you see reflected there, which is put our injection. And that's about 2.5 kilometers away from the center of the pit. And that's how we actually get the water back into the aquifer. A very successful operation based on a lot of extensive scientific research and test work and identification of what would be the best method of getting the water back into the aquifer. And this is one of the success stories within the geohydrological world, talking about a managed aquifer recharge. All the other colors, the blue, the yellow, and the orange, are the monitoring network, both upstream in the mine area and downstream, right down to Geelweg, where you see where we monitor. Akila took you through some of that. One of the other things that makes the collaboration between industry and public and NGOs was being the fact that we, in our license conditions, operate what we call a water monitoring committee. It's represented by number of stakeholders, both from government, local government, NGOs, local farmers, local community representatives. It's legislated, so in our license has to be there. They attend. We attend a meeting where we present all of our data and statistics every 6 months, and we present and we have robust discussions of how we're doing and what's the state of the dewatering and monitoring network, and is it effective or not, to minimize and manage the impact on the groundwater and thus on the Viguri. The data is extensive, and we're sitting in the world, and Albion and Akila would have indicated to you, we sit in the world of data these days, and we have enormous access to an enormous amount of data. And just the computing power that we sit with today makes it so much easier for us and gives us the ability to advance our understanding of how the aquifers work. Let me take you through what the pit looks like. So what you see here is, if you're looking at that slide, from left to right is the direction of mining. And on the top left-hand side, you would see the crest line. You would see there's a road here and a couple of open patches representing the boreholes. That's how close the dewatering boreholes sit. And then what happens is we mine progressively in ventures towards the bottom of the pit. And the color differentiation there indicates what we classify as overburden, which doesn't have any mineralization, phosphate mineralization in it. And the gray represents the phosphate ore deposit. That sits about halfway in the deposit. So from the top of ground level down to the top of the clay layer, which is where we stop, is about 40 meters. We take off largely 25 meters first of overburden. It initially gets stockpiled, and you would see in that stockpile dump that you will see from the R27. It gets stockpiled to create the void, and then we go into what we call rollover mining. And rollover mining means as we advance in this advancing phase, we then drive the material over and we deposit the backfill on the ready mined out area. And we progressively move the rock through the ore body in that way. How do we mine? We mine using conventional mining methods. So it's dump trucks and excavators. There's no drilling and blasting in this operation, and we're fortunate for that. That being said, we do incur hard layers of material. In that hard layer material, either effectively where we find that the phosphate, the conditions that existed at the time were such that we almost had phosphate cementation taking place. So we had to work through hard bands of phosphate and break it through in order for us to move it. We didn't need to do drill and blast. What is amazing here is that, and I keep every geologist or geohydrologist I come across, I say, guys, if you ever want a real life view of a 40-meter cross section where you can stand, feel, touch, and scratch, here is an opportunity. Because everything in the studies that have gone up until now, all around interpreting the drilling core that you've looked at, you've extracted the drilling core. Here you have an opportunity to look at slightly localized, that regional view of the variation that exists. The porous nature of this aquifer, I started off thinking it is convention, everything's the same, the water flows through this aquifer at the same rate. It couldn't be further from the truth. Because of the nature of the particles and the deposition method that was adopted, the particles change and they cause the water to flow faster, and it actually in some cases hinders the water that is flowing through. So not only do we have the opportunity here to have a look at what's going on, while we're mining it, for me, it's a wonderful opportunity for us to actually share with the educational space, also our scientific research. The boreholes range in different sizes between 5, 10, and 15 liters per second, and we are pumping out of the borehole presently as we speak at a rate of 160 liters a second. So the combined effect of all the boreholes, and we are re-injecting that into the borehole system. The borehole system was initially designed, you would have seen that nice drawdown curve that Albie showed. That borehole the system was designed for 400 liters a second. And we are using half of the injection boreholes at the moment, and the boreholes are taking on the water with pleasure. They're not in any way concerned, and is absorbing the water quite successfully. Just some other photographs on the left-hand side shows you what a typical borehole looks like. On the right-hand side is the injection tank. You pump all the water into that tank, and from there, gravity flows into these boreholes. We're not pumping the water into the ground, it's gravity flowing into the ground. Some of the challenges in any mining operation has challenges. So I thought I would just reflect to you, and this is my second last slide, is that in 2023, we had excessive water conditions, and those rains made life quite difficult. We also realized from the initial boreholes, based on the drilling, and we had pertinently told our drillers to say, when you get to the clay layer, you stop drilling. We realized that in some cases, the clay had formed layers and would be called perched aquitons. So they sit in an elevated, narrow band, and as a result, we hadn't drilled to the base clay. And as a result, you literally had water skirting underneath the boreholes into the basin of the pit and aggravating the waterlogged situation that you did. So we had to drill additionally to that. The ultrafine sand and the nature of this material is also led to, and it does continue to lead to problematic pumping, but nothing that can't be managed through maintenance. Like any borehole, if you're adding and you're pumping out iron-rich fine sediments do tend to occur. You can get a view of what it looks like. It looks pretty much like cholesterol in one's arteries. So you've got to clean that out. And this only happens through an ongoing maintenance program. So my last slide is more just a fun fact. To date, and earlier this year, we have pumped and re-injected the total of 0.8 million cubic of water, groundwater, out and back into the ground. We've expended electricity to pump that water. It has gone back into the ground in our attempt to say we don't make an impact on the aquifer. That's effectively if you fill a 1 meter diameter pipe, you stretch it around the world, that would mean the pipe length would be 40 kilometers. We're currently tracking a 45 kilometers. Or 1 meter diameter pipe is how much water will be pumped to that. That looks like a big number. And if you compare it to something like the Fourthly Dam, in terms of volume, it's probably a quarter of the Fourthly Dam. And I tried to get some big stats to keep it. I could be totally obsessed. The annual domestic water consumption in the municipality is about 3.5 to 5 million cubic meters a year. Just to give you an idea. And that effectively been happening since 2017. So thank you for your time. I appreciate this opportunity. Happy to answer some questions.